Welcome to the Cognitive Edge, where educators, librarians, technology leaders, and lifelong learners come together to explain or examine how people think, learn, and grow. I am Dr. Daniel A. Sabol, and today I want to talk about a subject that can make even confident students nervous, and that is calculus. So, for many students, the word calculus immediately brings uh, to mind complicated formulas, mysterious symbols, and difficult examinations. And they worry about pages filled with numbers that seem disconnected from everyday life. And some students decide that they cannot understand calculus before they have even entered the classroom. And I'm not sure where that came from, but calculus is not simply just a collection of difficult formulas. Um, at its core, calculus is the mathematics of change. So we're looking at rates of change. It helps students, uh, helps us basically understand things and how they move, grow, shrink, accelerate, accumulate, and respond over time. When we calculate how quickly a car is speeding up, we're thinking about calculus. When scientists examine how a disease spread, they use calculus. When engineers design bridges, aircraft, or computers and medical devices, they use some form of calculus. When economists study changing prices or businesses analyze growth or environmental scientists track changes in temperature, um, calculus really helps to describe what's happening. The problem is not that calculus has no connection to the real world. Um, the problem is that we often teach the symbols before we teach the meaning. And yeah, the symbols are important, but the meaning is even more important. And so students may be asked to calculate derivatives before they understand that a derivative represents a rate of change. They may be asked to solve integrals before understanding that integration measures accumulation. And when instruction begins with procedures instead of ideas, students may learn to initiate or imitate steps without understanding why those steps accomplish or what those steps accomplish. They can sometimes complete a problem correctly while having no idea what the answer means. And this is not mathematical understanding. This is mathematical compliance. Um, and if we want students to become confident with calculus, we must begin with experiences that they already understand. And imagine driving a car, okay, and you're kind of headed down a road, and your location changes as time passes. Your speed tells you how quickly your location is changing. Your acceleration tells you how quickly your speed is changing. That's calculus. Um, it's pretty straightforward. Um, a derivative measures how one quantity changes in relation to another. Um, so imagine filling a swimming pool up. Um, Water enters the pool over time, and each minute adds another amount of water. Eventually, all those small additions create the total amount inside the pool. That's also calculus, and it's again, a rate of change based upon one quantity. So an integral adds small quantities together to determine a large total. And these ideas are not beyond students. They are already part of the way students observe the world. The challenge is connecting those observations to mathematical language. Uh, Teachers should therefore begin by asking questions about change. Um, how quickly is something moving? Or how fast is something growing? Like the economy, or the change in the amount that a dollar's worth, or when is something increasing or decreasing, like imports and exports, you can show them. How much has accumulated over time? Maybe the amount of gasoline that has come into or out of the United States. Where does a curve become steep? Where does it flatten? These questions create meaning before students encounter formal notation. They're especially powerful. Graphs are very powerful because they allow students to see change. When you can see it, then you can entail or visualize it. But a graph is not merely a picture placed beside an equation. It's a representation of relationship. So students should be encouraged to describe what a graph is doing before calculating anything. Is the graph rising? Um, is it falling? You know, really, um, is it changing quickly, or is it changing slowly for that matter? Does it reach a maximum? Um, does it level off eventually? Is it volatile? What might the graph represent in real life? When students learn to interpret these patterns, derivatives and integrals become less mysterious. Um, a derivative really describes the steepness of the graph at a particular point. So an integral, it describes accumulated change, often represented by the area beneath a curve. So an integral describes accumulated knowledge, often represented by the area beneath the curve. I just wanted to repeat myself one more time about that. And the symbols begin to represent visual or visible ideas rather than arbitrary rules. Technology can also make calculus more accessible. Graphing software, simulations, spreadsheets, animation tools, and interactive mathematical platforms really allow students to manipulate functions and immediately observe the results. Students can change a number and watch a curve move. Um, they can compare a function with its derivative, which is really a big thing to do. They can see how small rectangles approximate the area beneath a curve. Um, they can slow down motion and examine changing rates, and also they can test predictions. Used effectively, technology can turn abstract ideas into experiences that students can explore. However, technology should not perform all the thinking. A student can really enter an equation into a calculator and receive the correct derivative without understanding why the answer is correct. And that tool may complete the calculation, but really the students are still not interpreting the results correctly. Um, what does the derivative tell us? Why is it positive in one region and negative in another? Um, why does a value of zero, or what does a value of zero represent? How does the answer connect to the original situation? Um, Technology should really help students investigate mathematical relationships, not hide them. Artificial intelligence creates a similar challenge. Um, AI can explain procedures. It can generate practice problems, demonstrate alternative approaches, and help students identify mistakes. These tools may be useful when students need additional explanations or opportunities to practice. Um, but students shouldn't not simply just find an AI tool and copy the AI generated solution. They should question it. They should examine every step. They should explain why the method works. Um, they should really be able to test the answer using another representation. They should really identify whether the AI misunderstood the problem. And in calculus, the reasoning matters as much as the final number. Students also need permission to struggle. Um, they need to understand that calculus often requires students to connect algebra, geometry, graphs, functions, and logical reasoning. Difficulty does not necessarily mean that a student lacks mathematical ability. It may mean that an earlier concept needs to be reviewed or that the current explanation does not match the student's way of thinking. When students become confused, educators should diagnose the source of that confusion. Um, does the student understand the concept but struggle with algebra? Or does the student misunderstand, or does the student understand the procedure but not the graph that he or she is looking at? Does the student know the formula but not when to really apply it? Does the notation itself create a barrier? There's a lot of notation in calculus. Saying try harder does not solve these type of problems. The try harder objective is, I don't know. Students really need focused feedback and a clear next step in what to do. For example, a student may not need 20 more derivative problems. A student may need 5 carefully chosen problems that demonstrate the relationship between the equation, the graph, and the real world meaning. More work is not always better work. Calculus instruction should also provide opportunities for revision. In many mathematical courses, students, they'll complete an examination, they'll receive a grade, they'll move forward. Their mistakes are recorded, but they may never be corrected. And this approach really treats assessment as a final judgment rather than part of learning. Um, Students should be asked to examine incorrect solutions, identify where their reasoning changed direction, and solve the problem again. Um, that's really the ultimate way to do it, is to struggle with it. They should really explain the mistake in words, what the error has conceptualized, and what they understand to be algebraic. Was the wrong rule selected? Was a negative sign lost? Did the student misunderstand the question? That happens quite often. Um, this kind of error analysis develops mathematical awareness. Um, a wrong answer is not simply something to erase. It's evidence that can improve the next attempt, as long as the teachers can also use collaborative problem solving to put the two together. Calculus is often presented as an individual activity in which students silently calculate answers, but discussing mathematics can deepen understanding. Students can really compare methods, defend conclusions, interpret graphs, and explain why a solution makes sense. And this helps develop the mathematical mindset. One student may understand the equation, another may understand the graph, and a third may connect the problem to a real world example. Um, it's pretty nice that we're able to form teams and use a three-team method. When students are um, when they explain their way of thinking, they make invisible reasoning visible. And this helps us as teachers identify misconceptions. And it also helps classmates see that there may be several legitimate ways to approach a problem. The school librarian can also contribute to calculus learning. Libraries support interdisciplinary inquiry. A librarian can help students investigate how calculus is used in architecture, medicine, robotics, economics, sports, astronomy, climate science, computer programming. The list that just goes on where this fits in. And students might research how calculus um, helps model population growth, or predicts the path of a satellite, or improves medical imaging, or designs safer transportation systems. This transforms calculus from a classroom requirement into a tool for understanding the world. Students should also be given opportunities to create with calculus. Now, this may sound a little difficult, but students, they can analyze the real data. They can design models. They can develop simulations. They could examine motion. They can study patterns within their community. So, for example, students could analyze changing traffic speeds in their school. They can examine the rate at which a local population has grown, or student energy use over time, or they can model how quickly information spreads through social media. When students apply calculus to authentic questions, the mathematics gains purpose. The goal is not to make calculus easy either. The real, some ideas, they should be challenging. The goal is to make the challenge meaningful and manageable as well, because we need to remember that students do have other classes and so forth, and they're struggling in multiple places. So there's major difference between productive struggle and unnecessary confusion. Productive struggle occurs when students really understand the goal, process enough background knowledge to begin, and really can make progress with effort and support. Unnecessary confusion occurs really when instruction is unclear or notation is introduced without meaning or prerequisites are missing, or students really are expected to discover complex ideas without sufficient guidance. So um, we have strong teaching, and it does not remove intellectual challenge, it removes avoidable barriers. So we also need to reconsider how we define success in calculus. Success should not mean memorizing enough procedures to pass an exam. Um, I know that a lot of students that's it's a big worry to have to think about doing calculus, but a successful calculus student should be able to really to describe change, interpret a graph, connect the formula to a situation, evaluate whether an answer is reasonable, and explain the thinking behind the solution. Um, Students should really understand that derivatives and integrals that they're connected, and one examines change at a particular moment, the other examines how change accumulates. But together, they provide a language for describing a world that is constantly moving. Um, this is why calculus matters. It's so very important. It teaches more than mathematics. It definitely teaches students to examine relationships and to teach students how to really notice patterns, and it teaches them to break complex problems down into smaller ones. Um, it teaches students to use evidence, test assumptions, revise their reasoning, and really see things from a different perspective, so to speak. But most importantly, calculus can teach students that difficult ideas, they really become understandable when they're explored carefully, represented in different ways, and connected to knowledge they already possess. So um, we should really stop presenting calculus as a gatekeeper designed to separate students who are supposedly mathematical from those who are not. Um, Calculus really should be presented as an invitation to understanding change. What change did we go through, or what change happened? Students do not need to fear it. They need to really get into it and see it and try it. Um, they need to discuss it, and they need to experiment with it, which can sometimes be daunting. They need to connect it to the world around them, and really, um, they need to be taught the meaning before the procedure. Um, they should be using technology to reveal relationships and allow mistakes to become learning opportunities, and also connect mathematics to authentic problems. Students can and will begin to see calculus differently. They may discover that calculus is not an impossible collection of symbols, which it's not. It's a powerful way of explaining how the world works. Um, and perhaps the greatest lesson is this: Students do not become good at calculus because they immediately understand everything. Okay, I'm going to repeat that again. Students do not become good at calculus because they immediately understand everything. They become good at calculus by asking questions, practicing purposefully, examining mistakes, seeking feedback, and trying again with a stronger strategy. This is how students become good at almost anything. I'm Dr. Daniel A. Sabol, and this is the Cognitive Edge, where we continue to explore not only what students should learn, but how we can help them become confident. We can also help them become independent thinkers. Thank you for joining me, and I hope that you have a lovely weekend. And just keep in mind that calculus is just about rates of change. Um, Sounds a little complex, but it's not too bad. All right. Talk to you soon. Thanks. Bye bye.